I do have some questions in office hours about these proofs with quadratics, and so make sure you've watched or maybe rewatch Continuity 3, the video. And now what I want to talk about, so in this function, we had the function x squared minus 2x plus 2, and we want to check that it was continuous at the point 3 comma 5. And in that video, we sort of worked through that, well, we know that if our input x is really close to 3, then we somehow want to make this quantity x minus 3 times x plus 1 smaller than epsilon. And we did some work, we had some questions, and in the end we sort of had this idea that, oh, well, if delta is smaller than 1, then we can make this quantity x plus 1 going to be between 3 and 5. And what was so important about that was that it guaranteed that x plus 1 in absolute value was going to be at most 5. And then at the sort of ta-da moment in our proof, this was going to mean that delta was epsilon over 5. So let's look at the proof. So our proof, let's go through it. So let's let epsilon be greater than 0. And let delta be any positive number smaller than both epsilon over 5 and the number 1. And I've got these two colors here, and in that video we went through where we used the fact that delta was smaller than 1, that was to give us this bound here, and where we used that delta was smaller than epsilon over 5, that was because we were going to multiply delta times 5, and of course we wanted that to be equal to epsilon at the end. But let's go over to Desmos. So here in Desmos we've got our function. So here's our function. We typed it in x squared minus 2x plus 2. I've got a equals 3, so this is a point 3 comma 5. And let's plug in a value of epsilon. So right now epsilon is 0.5. And what we can see is that whatever our value of delta is, it's not good. We've got this red region here. We've got inputs that are pretty close to 3, but their outputs are way up here. It's outside this allowable range. And so let's see what happens. Well, if we do delta divided by 5, so we go all the way down, so epsilon over 5 is going to be 0.1. I'm really slow at doing this. All right, there we go, 0.1. We see that it works, right? So epsilon over 5 happens to work in this case. And so if we go back to our video, you might say, well, why do we even need this 1? Won't epsilon over 5 work in general? Well, let's try it. What if we change epsilon, make epsilon even smaller? Say we make epsilon 0.3, and then when we divide that by 5, I guess that's going to be 0.06. Still green. So it looks like it's going to work if we just do epsilon over 5. Except, what if we try a big epsilon? So what if I try epsilon equals 100? And now I set my delta to be, say, epsilon over 5. So if I do 100 over 5, that's going to be 20. Let's zoom out to see what's going on. Yeah, it turns out epsilon over 5 doesn't work when epsilon is equal to 100. So we have to be careful in these proofs. So let's go back and look at it. So in our proof, we really needed both ingredients to work. We needed a number that's smaller than epsilon over 5 and that's smaller than 1. So just to double check, if we say maybe epsilon was 50. And then what do we need for delta? Well, our proof says we want a number smaller than epsilon over 5 and smaller than 1. Let's see if that works. So we need a delta. It's got to be smaller than epsilon over 5, so that means smaller than 10. And it also has to be smaller than 1. So let's do that. Let's make our delta smaller than 1. Good, we're green. So our proof does indeed work. So you may want to play around with this when you're working through some of the problems. This will be useful. Next week I'll be making some videos about uniform continuity. We can sort of explore that as well. Thanks for watching.